the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to linear algebra students who are just going through row reduction and echelon forms, specifically for those who have just finished up a lecture on the row reduction algorithm, because we're going to be using that right now. The important thing to note about this video is that all the information that we're going to go through here really is related to augmented matrices representing linear systems, because we're going to solve linear systems in this video. And of course, when you do that, you create augmented matrices out of them. We need a few definitions before we hop into this, and these will be brand new to you if you've never had linear algebra in the past. The very first definition is that of a basic variable. Variables associated with pivot positions in pivot columns are called basic variables. This is essentially saying that if you have an augmented matrix like I have right here, and you have a column dedicated to the coefficients of x, and a column dedicated to the coefficients of y, and yet another column dedicated to the coefficients of z, the variables associated with these pivots, the ones right here, are going to be called basic variables. Now, you may think, oh, that just means that all of our variables in our linear system are just called basic variables. X, y, and z in this case would be basic variables. However, that is not always going to be the case. For example, suppose that your augmented matrix ended up, after doing the row reduction algorithm, or after using the row reduction algorithm, suppose that your augmented matrix ended up looking like this. Now notice we have some pivots right here, here, and here. And notice that if you've used the row reduction algorithm correctly, all of these pivots are the leading elements in their rows. There are zeros both above and below these pivots, and they're staggered from left to right, top to bottom. So this is definitely a matrix that we've used the row reduction algorithm on. However, not all the variables in the associated linear system are called basic variables. Let's make our lives a little bit easier here and just say the variable that's associated with the first column is x sub 1, the variable associated with the second column is x sub 2, and so on and so forth down the line. If we refer back to the definition, variables associated with pivot positions in pivot columns are called basic variables. Well, I've highlighted our pivots, and therefore our pivot columns are these three columns right here. Therefore, our basic variables are x1, x2, and x5. Notice not every variable in the underlying linear system is considered a basic variable. Well, if we have a definition for what these basic variables are, what would we call x sub 3, x sub 4, and x sub 6? Well, that's where this definition comes in. Free variables. Variables associated with columns not containing pivots, which I would just call non-pivot columns, are called free variables. So going back to what I've drawn just a moment ago, we know x1, x2, and x sub 5, those are all basic variables. Our free variables are the variables associated with non-pivot columns, which is essentially all the remaining non-basic variables. So essentially you have basic variables and then non-basic variables, which we call free variables. And by the way, you will often hear me say they're free roaming variables. I have a habit of saying that, that's all. But why are they called free variables? And why are actually the initial variables called basic variables, those ones that are associated with pivot columns? Well, we needed a definition, so we just called those basic variables. But there is actually a reason why we call the variables associated with non-pivot columns free variables. So let's investigate why they're called free variables. We'll do this through an example, and then I'm going to introduce a definition partway through this. So write the following underdetermined system. I'll highlight that because it's probably new to many people. as an augmented matrix and find the general solution. Again, probably something a lot of people don't know. Identify the basic and free variables. Maybe I should start by telling you what an underdetermined system is. In a very basic sense, underdetermined system is a system with fewer equations than unknowns. So if you take a look at this system of equations, we have 1, 2, 3, 4, 5 unknowns. Unfortunately, we only have 1, 2, 3 equations. So therefore we have fewer equations than we have unknowns, and by definition we would call that an underdetermined system, mainly because you can't determine an exact solution for this system. Now let's talk about the general solution. What the heck is a general solution? Well, a general solution is an explicit solution to a system that might involve free variables. We know from our mathematical careers up to this point that you can have a system that has no solution, one solution, or infinitely many solutions. The no solution case right here, normally we just say it's the empty set. We don't have any solution. Some people say the solution does not exist or there's no solution. It just depends on what your instructor wants. The second system you see right here, the solution is actually 2, 2. The third system right here, well, if you take a look at both of these equations, they're the same equations. Actually, the second one is just twice the first equation. So they are the same equation. And in fact, any point that satisfies that equation right there will satisfy the second equation. That is, if x is 2, y is 2. If x is 3, y is 1. If x is 4, y is 0. And so on and so forth. There's an infinite number of solutions. And the way that we would write this out is actually in what we would call general form. And the general form would go like this. X is allowed to be some parameter t. This is called parametrizing the solution. And then y is therefore equal to the opposite of t plus 4. So whatever somebody selects t to be, y will just be the opposite of that plus 4. If t were 2, y would be negative 2 plus 4 or 2. If t were 3, y would be negative 3 plus 4 or 1. And if t were 4, y would be negative 4 plus 4, which is 0. And this would be the general solution. Now, I should state that this doesn't quite adhere to the general solution statement here, or definition that you see up above. In fact, in linear algebra, most people would write it like this. Y is equal to negative x plus 4, and x is free. It's a free roaming variable. It's free to be whatever we want it to be. This would be the general solution. It's sort of the non-parametrized solution. However, I think most instructors prefer a parametrized solution. Just ask your instructor what they prefer when you're doing your work. So now that we have somewhat of a decent idea of what underdetermined systems are and what the general solution is, just means write the solution, even though there might be some variables that are allowed to roam around and be free, write that solution. Let's go ahead and solve this system, and then at the end, write the general solution and also state the basic and free variables. It's actually not too bad. And let me start by putting this in an augmented matrix. And I want to draw your attention to that vertical pipe I put in there. That is generally what people do to tell the world, yep, I'm working with not only a matrix, but a matrix that represents a linear system hidden in the background. This is called an augmented matrix, and that vertical pipe generally tells the world that the variable terms are way over on this side, and the constant terms are on the right-hand side. So I just stole the coefficients from this system of equations up here. The other thing I want to draw your attention to is we've seen this augmented system before. It is literally the example we used in the previous video on the row reduction algorithm. So if you're needing to see the row reduction algorithm, I highly recommend look up my row reduction algorithm video, because I solved this, or basically row reduced this matrix down to this guy right here. So I'm just going to go ahead and copy this and paste it in our current problem, and then we'll go ahead and talk about the basic variables, the free variables, and the general solution. So via the row reduction algorithm, we get down to this. We had our initial augmented matrix, and now we're down to this row equivalent matrix right here. Now remember, the variables in our original problem were x sub 1, x sub 2, and so on and so forth. So this first column is associated with x sub 1. The second column is associated with x sub 2. The third column is associated with x sub 3. The fourth, x sub 4. And the fifth, x sub 5. I wasn't alternating colors there just to be cute. I was alternating colors because I want to showcase that these pivots, and therefore these pivot columns, are associated with the variables x sub 1, x sub 3, and x sub 5. So our basic variables in this problem are x sub 1, x sub 3, and x sub 5. On the other hand, the free roaming variables, or the free variables, are x sub 2 and x sub 4. These are the variables associated with non-pivot columns. So we've already answered without doing too much work. I just borrowed from our last session or our last video. We've already identified the basic and free variables. We're actually done with this sentence right there. However, we still need to find the general solution and write it as a general solution. So going back through this, I'll erase my highlighting here. And what you can do is you could, I suppose, if you want to, rewrite this as a system of equations. So our system would be 1x sub 1 plus 3x sub 2, let's see, plus 2x sub 4 is equal to 3. 1x sub 3 plus 2x sub 4 is equal to a negative 1. And finally, x sub 5 is equal to 0. Now notice, that very last equation tells me no matter what I choose, x sub 5 will always be 0. That's a nice statement right there. So I'll go ahead and list that down below. I'll actually say x sub 1 is equal to, x sub 2 is equal to. So I'm listing out what my variables are going to equal to. However, two of them are free. And when I say free, I don't mean like they've been given to us. I mean, they're literally free variables. So x sub 2 and x sub 4. So what I'm going to do here is, instead of writing x sub 2 equals, I'm just going to say x sub 2 is free, x sub 4 is free. Free to be whatever we want. And now I'll take that equation right there for x sub 3 and x sub 4. I'll solve it for x sub 3 to write it in terms of x sub 4. So x sub 3 is negative 1 minus twice x sub 4. But because x sub 4 is free, I will eventually at some point say, well, what if x sub 4 is 27? And then I can plug that in here. Or more commonly, what if x sub 4 is 0? And we'll do the same thing for x sub 1. So if you go up to x sub 1 here, or the equation with x sub 1 in it, if you've done everything right, each equation should only have at most one basic variable. We're going to solve for that basic variable, and then it might be written, the solution to that equation might be written in terms of free variables. That's totally okay. X sub 1 is equal to 3 minus 3x sub 2 minus 2x sub 4. And there you have it. This is actually the general solution. Now, there are a lot of other ways to write this, but I would probably say this is the best way to write it. There is a parametrized solution, and I should write that down because your instructor might require that. So let's pretend as though your instructor is requesting that you write your answers in terms of parametrized general solutions. If that's the case, just choose a variable to stand in for x sub 2 and x sub 4. For x sub 2, I'll choose s, and for x sub 4, I'll choose t. Now, this was a question that I had when I was a student. Why on earth would I choose another variable to stand in for a variable? In other words, why would I choose s to stand in for the variable x sub 2? Why not just call it x sub 2? There are legitimate reasons to do it, but I don't want to get too deep in or far into the weeds on that. So instead, I'm just going to say it's an instructor's choice. But let's go ahead and do this. X sub 1 is therefore equal to, well, we had 3 minus 3x sub 2, that's 3 minus 3s. And we had minus 2x sub 4, which is minus 2t in our case. It actually looks nicer with parameters anyway. X sub 2, like I said, is S. X sub 3 is -1 minus 2 x sub 4, that is -1 minus 2t. X sub 4 is t, and x sub 5 is, again, just 0. This parameterized or parametrized solution actually becomes important, I'll just say it right now, when we deal with vectors. So that's why you want to get used to being able to parameterize your solutions. So there we go. We've actually answered this question. We've written the solution to this, the general solution to this system. We've identified the basic and the free variables. Now, I stole a lot of my work from a different video, so it would be nice to see in this video one full worked out solution. It won't take that long. Let's go ahead and do it. Write the following overdetermined system as an augmented matrix and find the general solution. Identify basic and free variables. Overdetermined systems are kind of the opposite of underdetermined. Underdetermined systems have fewer equations than variables. Overdetermined have more equations than variables. A little dirty secret about overdetermined systems is that they often lead to no solution because you have way too many constraints. It's sort of like saying, to be happy, I have to earn more than $100,000. However, to not have terrible tax implications, I need to earn less than $250,000. However, I'd like a house that costs me a certain amount of money, so I need to make at least $300,000. So do you see what I did there? I put in a third constraint that counteracts my second constraint. So the more constraints you have, the more unrealistic a situation becomes. It's sort of like when you're trying to find your ideal mate and you have this laundry list of things, there's probably nobody that satisfies all of those features. So instead, you just throw out some constraints and say, I'm willing to deal with somebody who's an axe murderer or something like that. Nope, you're not, but let's just pretend you were. All right, so let's go ahead and write this as an augmented matrix. Great, we've stolen the coefficients, we've done all that. Now let's go ahead and start the row reduction algorithm. Start in the leftmost column, and of those entries in the left column there, just choose one of them that you want to be the pivot. I'm just gonna let that 3 in the upper left-hand corner be our pivot, and I'll use that to kill all the elements below. So writing out how I'm gonna do that, let's just go ahead and do that right now. So the opposite of row 1, add it to row 3, that'll kill off that 3 in row 3. And the -2 times row 1 plus row 4, well, that'll be -6 plus 6, which would be 0. So that gets us a 0 in row 4 as well. Let's go ahead and do that. Okay, we get down to this point right here. We have successfully taken our pivot and used it to kill everything below. Let's go ahead and go to the next sub-matrix, if you will, this group right here, and choose one of the elements from the leftmost non-zero column, which is this column right here. Choose one of those elements in there, one of the entries, and call it a pivot. I'm actually just going to take simply this guy right here and use it as my pivot. Let's go ahead and write down our action. And look what happens here. We have our 2 pivots. We have our 2 rows of zeros at the bottom. This is definitely in row echelon form. However, we'd like to get this to reduced row echelon form so that we can solve the system. That's actually why you go to reduced row echelon form. So let's continue forward. To get to reduced row echelon form, we'll start at the rightmost pivot, which is this guy right here, and we'll use it to kill everything above. And finally, we get to our last rightmost pivot. There's our pivot we just worked with. We're going to now focus on this guy, and we'd like to change that into a 1. So I will now finally divide that row by 3. Notice that I didn't divide the row by 3 until this moment. I avoid division as long as possible. I wait till the last moment to do any type of division because that often will introduce fractions early. So if you avoid that and hold on to the very end to force 1s in the diagonals, then you might be lucky and avoid fractions altogether. And there we go. That is our completely reduced augmented matrix. It's completely reduced down to reduced row echelon form. The pivot columns, which are associated with the variables x1 and x2, give us our basic variables. The column not associated with pivot columns, that gives us our free roaming variable. So let's go ahead and write this out. And in fact, when I write this out, let me go ahead and write it as an equation first, or a system of equations first. There's our system of equations. And now what I'm going to do is I'm just going to tell the world, guess what? X sub 3 is free. It's a free roaming variable. And therefore, x sub 1 is just 2 minus whatever x sub 3 is. And x sub 2 is actually 2 minus whatever x sub 3 is. If you want to parametrize that, that's, by the way, the general solution. If you want to write this as a parametric solution, then you could say x sub 1 is 2 minus t, x sub 2 is also 2 minus t, and x sub 3 is equal to t. That would be the parametrized solution. Very similar, right? What's nice about seeing the parametrized solution or the general solution is that you can now substitute any value you want in for t and you get a solution to the original system. For example, if t were equal to 0, that would imply one of the solutions, or the solutions associated with t equals 0, would be 2, 2, 0. If t were 1, well, that would imply the solution associated with t equals 1 would be 1, 1, 1. And you could do this all day long. It's an infinite number of choices. So there we go. We have written that overdetermined system as an augmented matrix. So check, that's done. We found the general solution. We've identified the basic and free variables. I should have written that down. The basic variables are right here, and the free variable is right here. Okay, so I sincerely hope that that made sense to you. I was just using the techniques actually you know from algebra, but with different language. We're building language as we move forward in linear algebra because this language will be used over and over and over again. So you just want to get used to it. So we're baby stepping our way in to linear algebra. All right. Hope this was helpful for you, and I hope to see you in future videos. Have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.